Hi there, so this is the fourth part of lecture 23 review of differential equation and exponential of a. So we have previously discussed the ut of expanding the ut, expressing ut in terms of the e80 and so on, and right now we want to know the series of e to the a t. So how do we define it in terms of this series? So in order to do that, there's a prerequisite knowledge that you need to know, which is the infinite series of e to the x. So this has the formula of x to the n over n factorial. So you will have 1 and x, then half of x squared, and 6, it is the third factorial, and then 4 factorial x4, and so on, and you will have, of course, this term. So we'll just have to substitute x with the at in this case. So we will have the identity matrix, which is the 1, and then the at, which is the x, and then plus at squared over 2 at to the cube over 6, and so on. And then there's also a way to express this term. So if you recall from previous review, we have this term of u0 is the x e to the big lambda x inverse u0. So this e to the at, we got that is equal to here, right? Because this is just u0 and u0. So we can also to just make it check, to confirm that this is true, that we can also derive this thing from the series. So how to do that is quite simple. So identity equal to s inverse s, and then you can convert a to the s lambda s inverse t times, and the same also happens here. So you can pull out those s inverse and the s. So inside we'll have just the identity, the lambda t, and the half of the lambda square t square, and so on. So you will have this. So this is equal to this exponent of to the power of big lambda t. So keep in mind that this is just the eigenvalue matrix with the lambda in the diagonal, and it also the same here, just square, and then this constant, and it's just the variable t, and in the end you will have those matrices, the same form, and they are the same thing. There's also another benefit of having this term right here instead of expressing it in this term, because it works for the case of repeated eigenvalues, and this term also converge, because as you see, when we have the n factorial here, we are dividing by the n factorial, and it gets really large, right? Because 4 factorial is like 4 times 3 times 2, it's like 24, and 5 factorial, I guess it gets to 100, and it just gets really fast. So eventually it will be like 0, and then somewhere it will converge to some finite value. So this term will converge, and it gives us like an alternative way to expressing this. I still don't quite understand about the example in the book. I will work on that, and I will post it once I understand. But let me know if you guys know better about it, where to find it online. Especially what I mean is the example number 4 in the book. Yeah, so that's it for the fourth part, and we will move on to the next one, to the last one next. Yep, thank you.